something with the resolution. Okay. Okay, fine. Thank you.
Okay, very good. So our final speaker is Alex Arenas, who's going to be
Okay.
talking to us about spreading processes.
Thank you very much. Thank you to the organizer for giving me the opportunity to present here. This is a presentation that follow up a bit of the presentation of Mason and also Ginestra, and it's about multilayer networks. And I will fix my attention only in two processes that are two dynamical processes. In my talk, there will not be any theorem, as you can assume, and there will not be simply about the structure. I am interested in to see the effect of having this kind of structure on the dynamical processes. Then I will take advantage of the presentation by Mason. Then I will not introduce so much the multilayer complex networks, and I will go to two particular processes. I will show what happens when you have a single dynamical process. In these terms, it will be a random walk, and I will assess the navigability of a multiplex structure. And then I will see how to couple two dynamical processes and see what are the outcome in the epidemic process, in particular in a setup where there is epidemics and awareness. Okay. Then, the interest of these multilayer networks, as has been already introduced, is because our world is formed of networks of different types of links, right? And these are usually coupled. These networks are usually coupled. Particular examples are those networks in which, for example, social networks, the same individual participates of several of them, okay, having different connectivity in each one of them. One of the problems that has been mentioned in Mason talk is about the interconnectivity. As Mark was asking, how can be that this guy, if it is here and it is here, cannot be connected to each other. I will say that it is connected, but as Mason said, it is the weight of the connection what varies, right? I mean, in this case in which the instantaneous information flow from one layer to the other, we will consider that it is the same individual and there is no interconnection, but essentially is an infinite interconnection between them, I would say. This is one case, and the other case, the other clear case are multi-transportation layers, okay? You have a city, and then you have places on the city that are areas, I don't know, certain streets, etc. And then you have, I don't know, the bus transportation line, the metro, the railway, etc. And this is a set of networks that are interconnected each other. My point is that it is interesting to study these networks. We need a lot of theory to understand better what is going on here, and this is the beginning of the analysis that I will present here and that many people is interested now. We have differentiated at least three types of these multilayer networks. The first type will be these edge-colored networks in which the same nodes have simply different types of connections. This is I don't know, same people, familiar relations, friendship relations, work relations, etc. Okay? Here we don't put the links. This is the case that Mark was telling how it is possible. I mean, not putting the links is the same that projecting all these networks and maintaining the colors, okay? Which is a difference of blurring out the colors. Then this is the case I will study the more, that is a multiplex network where I consider that there is a connection and there is a weight for this connection, okay? Imagine in the case of the transportation network, it would be the commuting time that I have between the layer of the bus stop, and the subway stop. Have to walk down, walk downstairs or whatever, right? And then this is the more general case of multilayer network that we can call interdependent networks or community structured network. Indeed, there is no difference between one of these representations and the community structure we have been seeing in the talk by Tiago, for example, right? Then my claim is that most of the technology that has been developed for community structure, if we take into account the different links that we have between these communities, it can become new problems, like, for example, the percolation problem that Ginestra was explaining before. Okay. Then I will start my first example that aims at quantifying something that we call navigability of a multiplex network, and this quantification will be by random walks, which is the most simple process that I can imagine. Then I will explore the network using these random walkers. We will quantify the coverage, the fraction of reachable nodes in a finite time, where a node is like a column node, okay? It would be an area in the city, for example. And this is what I call navigability from now on. And I will exploit the results of this measure in terms of dynamical resilience of the system, what happens if some links fail with this navigability or coverage. Then, essentially what we will have is this. I have layers, right? And the random walker can move within the layers, can switch the layers, and can make things that are pretty weird, okay? It's not exactly a random walk in 3 dimensions, because look, what we are doing is to have a discrete space in which we switch layer, but in this type of network where the nodes are the same entity, is the only possible switch that I have. I mean, I cannot switch directly, in this particular case, from node 2 to node 6 in the other layer, okay? Fine. Then, the approach is, let's write what is the master equation for the probability, what is the probability of B in a node J in a layer beta at time t plus delta t. And this can be decomposed very simple in the probability of staying in this node, having started at this node, the probability of switching from one layer to the other, alpha to beta, but in the same node. This will correspond to one of these transitions, right? The probability of jump, that means I am in the same layer and jump from one node to the other, or the probability of switching and jump, going from one node in one layer to another node in another layer. That is a path like this, okay? Then, having decomposed all this transition matrix, which is effectively a tensor, we can try to compute what is the coverage, which is a very simple exercise. Let's assume that we compute the average, the sum of all the probabilities to find the walker in a vertex I, regardless the layer. We introduce a supravector that is reminiscent of the supra matrix that Mason was presenting. I mean, a matrix that is the unfolding of the tensor corresponding to the multilayer object. And then with this prescription, we can write in matrix form the probability of node I at time t plus 1. We compute the probability not to find the walker in a certain vertex at a certain time, assuming that the walker started in a vertex J, which is given by this simple product of probabilities. Then we realize that this satisfies a recursive equation, which leads to this prescription of the variation of the probability not to find a walker in node I after t times starting in node J, right? But on the other side, we know that this probability follows this expression. This is the time evolution of the supravector of the probabilities according to the supra-Laplacian, the Laplacian of all the multiplex, okay? Then, putting this equation in the other one and substituting this expression, we have an analytical solution that reads like this. And now we can compute analytically what are the results on particular multiplexes. Here I present 2 layers of networks constructed with the algorithm by Barabasi-Albert plus a layer of Erdos-Renyi, or 2 Erdos-Renyi networks. And in all cases, the Monte Carlo computation, that is are the green points, the equation 2 that corresponds to D, and equation 3 that corresponds to an approximation of this when the largest, we keep only the second eigenvalue, are pretty okay with the simulations. Then, how can I use this to assess something about the system we are investigating? For example, we can try to for what is the resilience to failure in transportation networks using this measure. I will compute the coverage of the multiplex at a certain time, tau, larger than 1, in absence of failures, Then I will promote a fraction of nodes experience a random failure, and I will compute again the expected coverage after the damage. And I will define this ratio as the resilience of the multiplex. And I will do this in real data. We pick data from London, from the tube, from the overground, and from the DLR. And in this case, the connections are undirected and weighted. In the case of the tube, the weight is given by the number of different underground lights connecting to a station. That means that we have overlapping edges, like in the case by Ginestra. And we have the check-ins and check-outs of the Oyster car, a 5% sample for 1 week in November 2009. And then we can experience what is the dynamical resilience. I mean, what is the navigability in these cases, considering the separate layers or the multiplex. Here we see that the multiplex is always better in dynamical resilience than any of the layers in particular, which is telling us is a nonlinear effect what happens here, that you have more ways to go from one place to the other using the full multiplex, right? Here we did a comparison with the topological resilience with the fraction of nodes in the giant component, but this is not interesting in this case. What I wanted to say is that even though this seems to be trivial, first of all, we have quantified how resilient it is, and second, this effect turns out to be dangerous because this is a random walker, but if you put many random walkers and you take the problem of congestion, it emerges a new Bryce paradox in the problem. And it turns out that having a multiplex produces more congestion that doesn't having a multiplex. And this is a result we have recently published in Physical Regulators, but is a direct consequence of this dynamical resilience, which has the other counterpart. Okay, I don't want to spend much time. Then this is what we did with real disruptions, because getting at random some stations and eliminate it is not really what happens in the transportation system of London. What we did is to weight according to the oysters and retrieve data from Twitter. And then we have partial disruptions of lines, and we can put these real disruptions. And we try to assess up to which point these random walkers are a proxy of something more realistic, like an agent-based model following shortest path, okay? And here are the data, and I summarize this. Basically, the random walker prescription in the analytical formula is able to capture up to an error of 15% the navigability of the full system after simulation. Okay, I finished this talk, and I will give you a glimpse on these now two processes that concerns epidemics and awareness. Okay? The epidemics will be the abstraction of some contagion disease, and I will assume that there is some information in the system, and at some point the information in the system is about the contagion, right? And I want to use this setup to say something about this physical process where they both are interacting. The question is how does the spreading of this awareness affect the spreading of a disease. The setup will be a multi-layer network where the information spreading layer and the disease spreading layer are not the same. Okay? For example, in the disease spreading layer, I am assumed that I have a personal contact. I have the possibility to transmit the infection to one another. But in the information layer, it can be people that I know, that I call by phone, and is not a direct contact. Okay? In the simulations that I will present, what we did is that this information spread is larger than this in terms of density than the physical layer. But also we introduce errors here, but not to be one contained into the other. But in general, what we will do is the following. For the disease spreading layer, we will assume a simple SIS model. SIS model stands for susceptible, infected, susceptible model, in which if an individual is susceptible, it has a probability beta to become infected. If an individual is infected, it has a recovery rate mu to become, again, susceptible. In the other layer, what we will have is the information spreading layer. And in the information spreading layer, I will model the awareness the same way. we call unaware, aware, unaware, but this is an SIS model again, in which you have a probability lambda to a unaware person to be aware about the sickness, and then with a probability delta, this awareness, you forget, you don't care, etc., and then you are not taking any countermeasure because you are unaware. Okay? Then, in principle, what we have are 4 states that corresponds to this unaware susceptible, aware susceptible, unaware infected, aware infected. Okay? Even you can say that the unaware infected cannot exist, because if you are infected, you are aware that you are infected. But it's not always the case. There are these models in which you are exposed. That means that you are infected, but you don't show the symptoms, and you don't know. Really, you can count this also. Then, what is the coupling? The coupling is this probability of self-awareness. One individual that is infected with a certain probability get aware. You can set this probability to 1, and then this state is always infected, aware. Okay? And then this is the most important part. If you are aware, you can take some countermeasures, and there is a probability gamma that you get some fraction of immunization. Okay? According to this model. Okay, then there is another parameter that we introduce at the end of the model to be a little bit more realistic according to the referees, that is the influence of mass media. Okay? Like a random source of information, not random, I mean a source of information that randomly inform the different individuals with a probability m. Okay? Then here is the model. You have infected and susceptible individuals, aware and unaware in the layer of the information, and then we use this microscopic Markov chain approach that we invented more or less in 2010, in which we assess the individual probabilities of each node to be in each possible state at time t, and we calculate the spreading even beyond the threshold of the epidemic spreading pretty well in real networks. How it works is very easy. I mean, you write the probability of a node I to be infected in times t plus 1 by drawing these branches, these trees that are the probabilistic trees. Okay? You are infected with a probability mu. You get susceptible again with a probability 1 minus mu. You remain infected. And for the susceptible, the same way, where these quantities q's obviously are the product of probabilities of the rest of the neighbors that you have. You do this. Oops, sorry. What happens here? Okay. And you construct these different branches as terms in these equations. Okay? Then, in the case of the UAU-SIS model, what you have are these branches that become these equations that seem very long, but they are super easy, and you can solve this with a fixed point equation. You do this fixed point equation, you calculate the dependence of the critical infectivity threshold, then you assume that near the epidemic threshold there is no infection, it's just before the transition point, and then you can solve this to order epsilon, and you get a very nice critical threshold that depends for the infection on the adjacency matrix that you have in this infection layer, and the stationary probabilities that you will find for node I to be unaware and for node I to be aware in the other layer, with this gamma that I recall that was the immunization parameter. And this dependence is what you observe here. For example, for different values of beta infectivity in the disease and different values of lambda, let's say transmittability of the information, what we plot here are values of the total density of infected individuals. There is a transition between no infection and several values of the infection, and this is the critical lines of points that you obtain. The nice thing is that because of this interaction in the multiplex, it emerges this metacritical point, a point in which the dependence of the critical value of the infections starts to depend on the critical, of the values of the transmissibility. during this line they don't depend, and from now on they depend. Okay? Then we explore the different effects of the self-awareness, immunization, and mass media, and basically the main result, immunization is able to shift the onset of epidemics. I think I have the plot here, let me check. Yes, this is shifting the epidemics, which is somehow normal. The self-awareness make more individuals awareness in the information layer, and then you spread better the immunization. This is for the immunization. For the self-awareness, it doesn't affect the critical point, but the incidence. Okay, you see that the incidence is different. But the most interesting part is that the mass media, even with a very small probability, it shifts it makes the metacritical point, to disappear. Okay, that means that if you have mass media, even you have this periodicity in the information process, the metacritical point disappears, and the critical beta depends directly on lambda from the very beginning. Okay, I think I am in time. Those are my collaborators: Sergi Gomez, Malio, my postdoc, Albert, my postdoc, Mason here, and Clara, who did all these nice cartoons. And those are the papers, just in case you are interested. Okay. Thank you very much.
Question. Yes. Were those differential equations mean field in the sense that they assume that these probabilities, these events are uncorrelated?
Yeah, absolutely.
Okay.
So
have you tried doing actual microscopic simulations to see how close? I mean, on a random graph it should be fine, but...
Yeah, that's true. And in many of the cases that we have found, they are pretty close. But we are working in a pair approximation, because this is true. I mean, this is essentially a mean field at the level of the microscopic interactions. Yeah, right. And it is especially important when you have a lot of structure. For example, in lattices, where there are these dynamical correlations that emerge, there the differences are clear. But in our model and in any other mean field model, heterogeneous mean field, etc. But with higher order approximations, you can correct it. Yeah.
Yes. I'm always a bit worried if I see SIS on networks going on. Have you looked at SIR, where you get immune after?
Yes. But the problem there is that you have the fixed point of the recovery, and none of these interesting phase diagrams appear. I mean, yes?
Well, you can see something if the network is large enough, right?
Yeah, but at the end, because you are going to the stationary state, you go to everybody is recovered, right? Then you have a peak in time in which you have the fraction of recovers that you can plot. But I have to say something. For example, one of the things that we did, I mean, the aware model is like forgetting that you have to take the flu vaccine or something like this, right? But it's more normal if there is an epidemic that this is a rumor spreading, which is more akin to an SIR model, right? But if you put this SIR and SIS, and there is no this periodicity in the behavior, then it ends up that the result is much more trivial, let's say. It's like there is a mask of your network of physical contacts that are already immunized because they are aware at the end of the process, right? Then the other thing is that if instead of having this stationary state we do something time dependent, then for sure it will be interesting to see how the different time scales in both interact each other, which is something that in the multiplex will have an effect for sure.
Do you expect the result to change if you have multiple media sources?
I don't expect to change, because effectively what the mass media is doing is, with a certain probability, any random node get aware, okay? And this is like putting seeds for the awareness, which, if the network is a little bit unstructured, a little bit homogeneous, for example, it favors the expansion of the awareness very, very fast. Then multiple channels of media I will say that will amplify this
What
phenomenon,
if
right?
they counter each other?
Ah, okay, that's a good question. Yeah, yeah, this is a good point. Look, okay, in this case, I have awareness and epidemics. Let me say something. If instead of awareness and epidemics, where one of the dynamics is trying to avoid the other, you put two SIS, being these two diseases, that one, let's say, improve the other. For example, having diabetes and I don't know, hepatitis, I think, or HIV and hepatitis, that you reinforce each other. Is the same. Is the same, but all the phase diagrams are the other way around, right? Then, if the mass media can be contradicted, then you put like positive and negative impulses. The net effect of this will be the responsible of the awareness. Let's say the average between -1s and +1s. At the end, what you receive is positive or negative, and then you can have both effects.
Any more questions? If not, then let's thank Alex and all the speakers.
Thank you.